Hello, everyone. So today's warm-up question features definitely not a true life story. This does not apply to me at all. This is something that I just randomly came up in my head. So let's say hypothetically, in one hypothetical world, Mr. Wu is trying to get swole. He's trying to get yoked. He's trying to get huge. He's trying to get very muscular. However, he doesn't actually want to work that hard. He's one of those people who wants the gains without actually having to put in the work. So the question I pose to you is, what are some ways that Mr. Who could lift a 50 Newton weight without actually having to apply 50 Newtons of force? So how can Mr. Who lift weights without actually having to essentially lift weight? Um, so I want you to think of some ideas that of how I could lift a 50 Newton weight without actually having to lift 50 Newtons of weight. So one common potential idea that some people in first period have said and some people in second period have said so far are steroids. So here's the thing about steroids. What happens with steroids is you get huge, which I guess is sort of the goal here, but you still have to apply 50 Newtons of force. It may be easier for you to do so because you are unhealthily large, which I cannot condone the usage of steroids or any other performance enhancing drugs. But the thing is, if you are on steroids, you get huge and you get very muscular unhealthily, but you still have to actually lift, you still have to actually apply 50 Newtons of force. So it doesn't really quite, it's not, you're not really, it doesn't really quite, it's not quite what we're trying to accomplish here. It's a good idea though. It's a good idea though. Are there any other ideas of how you can lift a weight without actually having to apply that much force? So what are some ways that humans use to essentially uh, cheat gravity or cheat other force? So we have a couple of ideas so far. We have a couple ideas with using a lever, or putting a lot of small weight on one side, the other side of the lever. He could also use wheels and make a 2-to-1 ratio. So he doesn't have to apply the force. There are a couple of ideas here so far. Are there any other ideas as to how I could lift the weight without actually having to apply that much force? Put one weight on each arm. I think I see what you're saying. So if you put one weight on each arm, so let's say each weight is 25 newtons. So each arm would have to lift up 25 newtons. So in the end, you still are lifting 50 newtons. So I think that's a good idea, unless I'm misinterpreting what you're trying to say. Yeah, because if you put one weight on each arm, each arm still has to lift 25 newtons. So in the end, you're still lifting 50. So I guess each arm is working less, but our goal here is to just work less in general. Um, you could hire a crane. That actually is a decent idea. Um, actually, we have a couple of, so we have a couple of other good ideas here. We have a system of pulleys or a system of gear ratios. We have use a pulley system. The more pulleys you use, the less force you need to apply, but over a longer distance. These are also some really good ideas. There are also, so any other ideas of how I can, we'll take another minute or so, how I can cheat my gains. You could take some dollars out of your pocket and pay someone to carry it for you. Ah, great idea. Wow, that's honestly, yeah, that's a good idea as well. Some form of system that'll give you enough leverage so that you do not have to apply for units, of course. Um, yes, so the essence is we are trying to essentially cheat physics here by trying to, there are ways that you can lift nuke weight without actually having to apply that much force through some, let's just say, magical ways, which we will explore today. So there are a few magical ways of what we can accomplish this goal. Unfortunately, so this is something that someone in first period pointed out. So you cannot actually cheat your gains here. So if you're trying to get swole, you do actually have to lift the weight. So just lifting the weight without having to, if you're trying to cheat the system and lift weights without actually having to apply that much force, you still don't get the gains you want. So basically, you can't cheat to get your gains is the moral of this question. But you could still lift weight without actually having to apply that much force, which is something we will be exploring today. So today we will be exploring the topic of pulleys and forces in equilibrium. Oh, yes, you could also use a ramp or some kind of screw thing. Basically, you're trying to apply less force over more distance. Wow, that's actually a really good idea too. I feel like I've already taught you guys this, even though I haven't taught you guys anything about this, but that's really interesting. Yeah, that's also some good ideas. So today we're going to be exploring pulleys and forces in equilibrium. Basically, we're trying to explore this idea of working smarter, not harder, because we are physicists. That is what we do. Okay, so the first thing we're going to talk about is this idea.
You can't see the slides if you're trying to show us the slides right now.
That is.
We could see them until like a minute ago and they disappeared.
That is so. Here we go. Thank you for letting me know. That's very helpful. Okay, so now I believe you can see it. Now I believe I have fixed that. Okay, so what we want to talk about first is we want to talk about this idea of cheating the system, of working smarter, not harder, of being able to get more out of doing less work. So this is this idea of something called mechanical advantage. So what is mechanical advantage? So a huge part of engineering and physics is basically utilizing the mechanical advantage of machines to produce more force than the force you are putting in. So basically, I put something in and I get more out. So it's like, imagine if I put $1 in a vending machine and I get $2 out. So that's basically what mechanical advantage is. And the idea is we want to design machinery that can allow us to do that. So what is mechanical advantage as like, what is it actually? Or like, what is the more specific definition? So the more specific definition is basically just measuring the ratio of the force being applied to the force being produced. So if I apply 100 newtons of force to a machine and the machine outputs a force of 200 newtons, I would have a mechanical advantage of 2. So basically it's just measuring how much force is the machine producing relative to the force you are putting in. It's like a force multiplier essentially. I put something in and I get more out. And that is what mechanical advantage is. That is what we're trying to do essentially. We're trying to design equipment, machinery that allows us to produce more out of less. So this sounds like something that is way too good to be true. How this honestly, if you were to think about it, this honestly sounds like it breaks so many rules of physics. But it actually works, and because this is not, it actually does work because there is a drawback for having this magical way of producing more force that we will talk about in a second. I know some people have already pointed it out. But there is a drawback to getting more force out, and that drawback is it takes more distance to do that. But we'll talk about it in a second. Basically, the main idea is we want to produce machinery that allows me to get more force out of force I am putting in. So there are a bunch of different ways that us humans use to essentially cheat the system. There are five, there definitely are more, but these are the 5 main ways. I think we actually hit all 5 of them. That's actually really impressive. I was only expecting for us to maybe hit 3 of these. So I'm actually really impressed that we hit all 5. So these are the 5 main systems that us humans use to cheat the system. We use pulleys, we use levers, we use gears, we use screws, and we use ramps. So we've already discussed ramps. We will discuss pulleys today. Levers and screws. We may talk about levers. I'm still thinking about whether or not we'll hit levers. We may hit levers. We won't hit screws, but screws is interesting. And I think in a different, in like APC, you might hit screws. Screws is really interesting as well. And I don't think any physics class will really hit gears. I think gears is more of an engineering class. So we will have at least 2 of these, maybe 3. But you will see how this works. Yeah. So the main idea is these are all the ways that us humans have developed to work smarter and not harder. So what I want you to do now is right now we are going to examine the first way we're trying to use to cheat the system. We're going to think about the equipment that we call pulleys. So what I want you to do is in the Zoom chat, I want you to write down as much as you know about pulleys. So I'll write down as much as you know. So this might include where you might have seen one before, where you might think one exists, where you think they're used. This may also include how you think they might work, or they may include what you think they look like, or I just want you in the Zoom chat, or just write down, or just message me or message the group, however much you know about pulleys. So where do you think you might see a pulley? What do you think they might look like? How do you think they might work? What do you think the purpose of a pulley is? There are a lot, we see pulleys all the time, and I want you to see if you can make the connection and think about where you might see pulleys in your daily lives. So in the Zoom chat, where do you see pulleys? Why might they be used? So I used a pulley to go window to neighbor with my neighbor that held a bucket. So we used the bucket to give each other candy when we were younger without our parents knowing. That's actually really clever. That's actually wild. That is wow. That is some real physics for that. Something that I feel like sometimes I don't give you guys credit for. It's just how clever you guys are. I don't think I've ever used a pulley in my entire life. So I'm really impressed that you used it when you were a kid to give each other candy. That's actually really impressive. I don't know. I would love one day I'll figure out how you learned it. That's really cool. So pulleys are used to drag the sails up on a boat. That's actually really cool. That is 100% true. This is something that I didn't really realize until maybe yesterday or maybe a few days ago. That pulleys are used to drag the sails up on boats. That is 100% true. That is really, really cool. And it's a really good example of where pulleys are used. So pulleys make it easier to lift heavier weights. 100% true. That's what the purpose of pulleys are. Pulleys were used on older ships with sails to make it easier to deploy and fold sails. Yes, 100%. I'm actually really curious as to how you guys learned that pulleys are used to drag the sails up on boats. Maybe you're just more observant than I am. I've watched Pirates of the Caribbean 100 billion times, and it never really occurred to me that pulleys were used to drag the sails up. Honestly, I'm going to be honest with you. As a physics teacher, I should probably be more aware of pulleys, but I'm kind of an oblivious person. So I honestly don't really consider where pulleys are used. So I'm actually really impressed that you guys know so much about pulleys. Pulleys it's a loop that takes a rope from one side and there's an output of rope from the other side, and allows us to pull objects up by pushing the rope down. Yep. When I think of a pulley, I picture a suspended rope over a wheel. I know they're often used in construction. Yep. You actually had to put the sail on the boat. That is wild. That is wild. That is really cool. That is really, really cool. Yeah. I am actually, that is, yeah, wow, I never, that is really cool. I just don't have, I'm just kind of speechless here. That's really cool. In a pulley system, the more pulleys that are used, the less force is needed to move an object. However, you need to pull over a longer distance. That is pretty much a very quick summary of pulleys. We will watch a video on that, but that is a really good summary of pulleys. A single pulley will not help you that much, but in a system, they can be effective. If the pulley are stationary, then they again are not effective. But if they're movable, then as you pull, the chucks come closer together and they need to pull longer to get the same distance. This distance over time is the way is distributes the force over time. I use them a lot in robotics. That is really cool. Honestly, yeah, if you use robotics, then if you do a lot of robotics, then you do a lot of then you will use a lot of pulleys. It basically is a weight pushed down by gravity to pull something up. Yeah, pretty much. Yeah. So I'm honestly very impressed with all the answers you guys shared. That's honestly super impressive. So I don't really have anything else to add because you guys pretty much have some really good ideas. However, if I don't have anything to add, we have our dear friend Bill Nye, the Science Guy. So how many of you have actually watched Bill Nye, the Science Guy? So this was definitely
Go
yeah.
Bill.
The homie.
No, yeah. So
I
Bill Nye-
only watched him on ERB, if you know them.
ERB. What's ERB?
Oh, Epic Rap Battles. His image super cool.
Okay.
That's the only way. That's the only place where I learned about Bill Nye.
Okay, yeah. Bill Nye the Science Guy is something is a staple of my science education. I don't know if it was of your science education. This may be a generational thing, me being of a completely different generation and being much older than you guys. So Bill Nye the Science Guy is something I watch all the time. And even in my AP Fit science classes, I watch Bill Nye the Science Guy. So we will watch a video from Bill Nye the Science Guy. Bill Nye is the GOAT. I agree, he is the GOAT. We watched it in middle school. Yes, we did. I did watch it in middle school as well. I'm glad you watched it as well. This is something we will watch as well. I think the target demographic of this is probably not high school physics, but I think it's a really good video. And so we watch a video featuring our dear friend Bill Nye the Science Guy. Bill Nye is here, but he actually doesn't make a huge appearance. Most of it is instead actually other stuff.
The pulley. The pail of water that Jack and Jill had to fetch was not on top of the hill at all. It was actually at the bottom of a well. Unfortunately, it was too heavy for either of them to pull up. What they needed was a simple machine to give them a mechanical advantage. No, the inclined plane doesn't help. Nor does the lever. Nor the screw. What other sorts of machine are there? Ah, yes, the wheel. But what's Jill doing with it? She is arranging the wheels so that it will revolve on an axle stuck in that post. Very good. Jill's just rediscovered another sort of simple machine. A wheel that instead of being all of a piece with its axle, can revolve freely around an axle. Since this type of wheel is used mainly for pulling things, it's called a pulley. And Jill can hitch the rope around it and use it to pull. No, Jack can use it to try to pull the pail of water up. That's funny. He needs just as much force to try to pull the pail of water up this way as he did trying to pull it up the other way. I wonder if there's a better way of rigging the pulley. Amazing. How did Jill manage it? Both she and Jack only had one pulley to work with, and yet Jill was able to pull up the pail with half the force that Jack needed. Well, when a pulley is set up like this, it's called a single fixed pulley. All it does is change the direction of your pull, but it doesn't reduce the force you need. But when a pulley is arranged like this, it's called a single movable pulley, and it halves the force you must exert, because the pail of water is now, in effect, being lifted by two ropes instead of one. It's as if two people were lifting the pail, and it looks as if we're getting something for nothing again, doesn't it? But of course we're not. If we compare the distance that Jill raised the pail with the amount of rope she pulled, we see that it's the same old story. What she's gaining on the force, she's losing on the distance. The distance that she pulls the rope is twice the distance that she raises the pail. But the way Jill used the pulley is still twice as effective as the way Jack used it. There are lots of other ways of combining pulleys. The pulley system that Jill finally rigged up for herself. She had to pull the rope 3 meters for every meter that she raised the pail of water. In a sense, she'd become 3 times as strong as Jack. And now you know why Jack fell down and broke his crown.
Bill Nye the Science Guy.
Now this rope is attached to a crane. And a crane uses pulleys. Simple machines. Of course, they're big simple machines, but they're simple machines. Science!
Say you're building a treehouse and you needed some stuff. Say the stuff was really heavy. What would you do?
I'd use pulleys. A pulley makes things easier to lift because it spreads the work. See this rope? Before it just used to go from me to Cammy. But now it goes from me to Cammy to me and then back to Cammy. Now she's gonna have to pull a whole lot more rope to get stuff up here.
But more rope means I won't have to work as hard each time I pull down. So now I can lift something he can't. Here it comes.
With a pulley, she can pull really heavy stuff all the way to the tree fort.
Pulleys. No sweat.
Back in the 1800s, all these cable cars used to be pulled by horses. Okay, the cable cars operate by a bunch of levers and pulleys, which are very simple to operate and maintain. Now I'll take you down below and show you how the grip works. These are the giant pulleys that pull the cable underneath the streets of San Francisco. There's many cables and pulleys that take them around curves and up and down the hills. We're in the sand. Oh.
Okay, you're on.
Come on.
Absolutely.
Sailing made simple by simple machines.
Well, thanks for watching. See how simple machines make our life a little easier. And of course, a lot more fun.
Wow, great video. So someone back in the day had to have thought about the idea of using a wheel to move stuff. I don't really know who thought of that idea, but it was a really good idea. So if any of you have an idea like that, you should definitely do it. That's pretty cool. So one of the things that they talked about in the video was something called a single fixed pulley, which is probably the most basic pulley that you can use to pull something. And it basically just involves using one wheelical device and you attach like a little rope over it to pull something, and it sort of changes the direction of the pull. So here, in this particular question, we are examining this kind of pulley, the single fixed pulley. So where might you see a single fixed pulley in real life? So probably the best example where you might see a single fixed pulley is if you're going to the gym and you are trying to do the tricep rope pull down. So it's the one where you have like the 2 ropes and you're like pulling it down and you're like working your triceps here. So that one is a single fixed pulley. You have a weight on the bottom, there's a little wheel on the top, and you're pulling down to lift the weight up. That's why it's called a pull down. So it uses a single fixed pulley to try to lift a weight. So what I want you to do is to quickly figure out how much force you need to apply to lift the 2 kilogram weight at a constant velocity using a single fixed pulley. And then what would the mechanical advantage of this pulley be? So you can draw a free body diagram for the weight. So it'll take a few minutes just to quickly work this out. How much force you need to apply to lift the 2 kilogram weight at a constant velocity. Okay, so let's take a look at this single fixed pulley here. I just drew a very quick diagram here. We have a weight floating around a wheel, and you pull the rope down here, make it go up here. So let's try a free body diagram for the weight itself. What are the forces acting on the weight? So as usual, you always have the force of gravity pointing straight down. Gravity of force is optics. However, we also have something pulling the force, pulling the weight up, and this is just the force of tension in the rope. So the weight being pulled up with the force of tension, and it has the force of gravity pulling it down, and that's pretty much it. Because there's only three forces acting on. So how do we figure out how much force we need to apply and all these things? So the first thing we want to do is we first want to identify that we are pulling the weight up at a constant velocity, which means that the sum of all forces in that direction is going to be zero. The net force in that direction is zero. This is a one-dimensional problem. All it's doing is going up and down. So I'm going to ignore the x direction here, and I'm only going to go y direction. So in here, the sum of all forces in the y direction is going to be zero, and this is because it's going to have a different velocity. There's no acceleration at all. So what is the sum of all forces here? We have two forces here. We have force of tension going up. And then we have force of gravity going down. So the sum of these two is zero, which is just a long-winded way of saying that the force of tension is going to equal force going up to equal the force going down. That way there is no acceleration. So the force of gravity going down is just its mass times gravity, which is just 2 times 8. So let me talk this equation. So in order to lift the object up, we need to apply this force. We need to apply magnetic force. And in this problem, we are also applying 19.6 newtons. So we need to apply 19.6 newtons, and we are applying 19.6 newtons. So for this particular one, there's not really a mechanical advantage here. Basically, this particular type of pulley, there's no sort of efficiency benefit. There's no efficiency benefit. I guess the main benefit is that it's easier to push things down than it is to pull things up, or because you can put your weight, because you can put your weight into it. But there's no technical benefit for using it. Like it's easier to exert more force pulling something down, but you still have to apply the same amount of force. There's just no efficiency benefit. There's no real technical advantage. Right? You need a certain amount of force, and you are still applying that. So this machine, this pulley, is not creating more force. There's no real benefit for this. The pulley, all this pulley does is it changes the direction of the force you need to exert. So that is the first kind of pulley, single fixed pulley. The other kind of pulley that we sort of examined in the video is something called a single movable pulley. So a single movable pulley is a pulley that goes up with the actual object. So that's why it's called movable, because as the object goes up, the pulley goes up with it. So in this particular picture here, you have the pulley on the orange pulley on the bottom, and as the weight goes up, that pulley goes up. So what I want you to do here is I want you to figure out how much force you need to apply in order to lift the 2 kilogram weight at a constant velocity. And I want you to figure out what the mechanical advantage of this pulley be. What would the mechanical advantage of this pulley be? So this is going to be very similar to what we just did. except this time, the benefit of a single movable pulley, I want you to look at the weight here, and I want you to look at how many, essentially, how many ropes are pulling the pulley up, pulling the weight. Last time we only had one rope. I want you to look at it now, and I want you to look at how many things are pulling the pulley, pulling the weight up. Okay, so let's take a look at this pulley here. So in this particular case, we have a pulley. So basically, the thing about a single movable pulley, as the weight goes up, this pulley goes up with it. This pulley stays stationary. So this one doesn't move. Doesn't move. So as we're pulling this down, this whole system goes down.
The camera's set on your slides and not.
Oh, yes, sorry. There we go. Okay. So this is a single movable pulley. As this weight goes up, the pulley goes up with it. This thing stays stationary. So as you pull this down, this whole thing goes down. So let's try a free body diagram for this. To visualize what's going on. So as usual, you always have the force of gravity going straight down. And then this time we know that it's being pulled up, so we know that there are forces pulling it up. So in this case, we actually have two ropes pulling up. So that are going to two forces of tension. It can be tempting to describe this as just being one force of tension here. I can be very tempting. But the thing is, it is being pulled by two ropes, and each one of these ropes is pulling it up. Right? These two, it's not one rope is pulling it up, it's two ropes that are simply pulling. And these ropes are going to have their own tensions. Now, in this particular problem, because the whole system is just going up at the same time, the two tensions are going to be equal. So I'm just going to write down that. And you will actually explore later on today that sometimes ropes can have different tensions in the same system. But within the context of a pulley, a lot of times you'll find that they will be the same. So we have two forces of tension pulling up, and then one force of gravity pulling. Now, the general setup for solving for the force that we need to apply is still going to be pretty much the same. The sum of all forces in the y direction is going to be 0. And this has not changed. The only thing that has changed is the fact that we've replaced the old pulley with a pulley with two groups. So now it's being pulled like this. So sum of all forces in the y direction is going to equal 0. And there's no static constant velocity, no acceleration. So what is the sum of all forces in the y direction? Well, we have the force of tension going up. We have another force of tension going up. And then we have force of gravity coming down. So essentially what happens is that we have two times the force of tension going up, and this is going to equal the force of gravity. So the force going up is equal to the force going down, and the force going up is 2 times. So what this means is that the force of tension we need to apply is just going to equal the force of gravity divided by 2. So that makes the force of tension we need to apply is so you need to apply this, you need to apply I will only apply so essentially the machine, the pulley, is turning our 9.8 into a 19.6. So this actually would give us a mechanical advantage of 2. So you don't need to know how to calculate mechanical advantage. The reason why I'm introducing this terminology is I want you to understand that the point of a pulley is to reduce the amount of force you need to apply. The system still needs 19.6 newtons of force with the force of gravity, but the pulley is essentially doubling the amount of force we are putting in. So we are putting in 19.8. The pulley is turning it into 19.6, and then that 19.6 we can use it. That concept of multiplying the amount of force we are actually putting in, that's something called mechanical advantage. In this case, the mechanical advantage is 2, because the pulley is essentially doubling the amount of force we are putting in. Shouldn't there be an arrow for the mass going down? I'm a little unsure what you mean. You mean like the force of gravity going down? Or do you mean like there's the arrow here? On the free body. Yeah, that's the force of gravity. So we're looking at this mass here. So this mass is being pulled down by gravity. It is a down mass, and then it's being pulled upwards. So there is a downwards arrow, and that downwards force is the force of gravity. We're pulling on this side, and the mass is pulling up on this side. Okay, no problem. Yeah. Cool. Okay. So that's what happens if you have a double pulley, or not double, a single movable pulley What happens if we start doing something even more wild and we have even more wild stuff? Okay, so yes, I'm well
I
aware
have
of
a
this
quick,
picture.
I have a
Go ahead.
quick question, which
Go
is,
ahead.
you know, the angle as a person pulls rope from the pulley, does that affect the force?
The angle at which you pull it in.
For example, here's the first picture, it's straight down, and the last picture, it's with an angle.
It's in this particular case, it doesn't matter.
Okay.
You will find that in other cases it does matter. The reason why is that if you pull this at an angle, if you pull something at an angle in this particular case, the angle well, the only thing that matters is the force that you are applying, the magnitude of the force you're applying, and that will have a 1-to-1 ratio with the tension in the rope. You will find that in other cases that we'll do later today, the angle does matter. But the angle at which you're pulling a pulley is not mattering.
Okay, thanks.
Okay, so in this particular case, I know well aware the picture is not very clear, and I'm well aware you can't read the numbers. I can't read the numbers either. What I just want you to look at is just there are essentially 5 different pulleys here. The first one is a single fixed pulley, which we looked at earlier. The second one is a single movable pulley, which we looked at later on. And then the other 3 are just even more bigger pulleys. So what I want you to do is I want you to quickly identify what are the mechanical advantages of these 5 pulleys. And I want you to see if you can try to figure out what the pattern is. What determines how much mechanical advantage a pulley might have? So the single fixed pulley just has a mechanical advantage of 1 because there's no advantage for using it. The second one, the single movable pulley, has a mechanical advantage of 2 because it essentially doubles the amount of force you are putting into it. What about the third one, the fourth one, and the fifth one? So what are the mechanical advantages of these 5 pulleys? So the first pulley has a mechanical advantage of 1. Second one has a mechanical advantage of 2. The third one has a mechanical advantage of 3. The fourth one has a mechanical advantage of 4. And the last one has a mechanical advantage of 6. So what determines how much mechanical advantage something has? What is the pattern here? The pattern is that the number of ropes, essentially the number of cables that are pulling an object up, determines essentially what the mechanical advantage is. So the first one, you only have 1 rope, so the mechanical advantage is a 1. The second one has 2 ropes, so there's a mechanical advantage of 2. So essentially 2 ropes doubles the amount of force you are putting in. 3 ropes essentially triples how much force you're putting in. 4 ropes quadruples how much force you're putting in. And the last one has 6 ropes pulling the object up. So that essentially hexa multiplies your force. However, each one of these pulleys requires more and more and more amount of rope that you need to pull in order to lift the same object up. Because essentially you are spreading the amount of rope over that you are pulling over multiple pulleys. And so you need to pull the object with more rope in order to lift it up. So it's a compromise. More rope, less force. So what is the key takeaway here? The key takeaway is I want you to recognize that the amount of rope, if you're ever looking at an object in a pulley and you need to figure out how much force you need to apply or is being applied, you should look at essentially how many ropes are pulling the object up. Okay. So here is another thing that we will talk about, and this is the concept of something being at equilibrium. So in all of the previous things we've been looking at, all of the weights were being pulled at a constant velocity, which means that the net force on these weights are 0 because it's being pulled at a constant velocity. Because technically nothing about the system is changing, because technically the velocity isn't changing, because nothing else is changing, we can say that the system is in equilibrium. So when something's in equilibrium, right, it just means that the net force is 0. In this case here, the object is moving at a constant velocity. So we can say that the system is in translational equilibrium. Translational, basically moving equilibrium. If the weight was stationary, we would say that it is in static equilibrium. So the takeaway here is that in the previous systems we were looking at, they were all in translational equilibrium because the object is moving at a constant velocity and it's not accelerating or anything. The reason why I'm using the word equilibrium, so the word equilibrium is honestly, we've been using equilibrium pretty much a lot. This is just a more scientific definition of it, I guess. At any time we've said that the net force, the sum of all forces is 0, we've actually done this a lot of times. Every time I've said that the sum of all forces is 0, I basically said the system was in equilibrium. So honestly, that's probably what I can just start, you can just start saying, instead of saying the sum of all forces is 0, you can just say that the system is in equilibrium, so we know that the sum of all forces should be 0. So I think that's probably a better way of looking at a problem. You can look at a problem and say, is the object in equilibrium? Is there a net force in any direction? Is it accelerating somewhere? If it is in equilibrium, then you know that the sum of all forces should be 0. If it's not in equilibrium, then you know that there should be a net force in one direction or something. So basically, forces are said to be in equilibrium when the net force in the system is 0. When there's no overall force, when everything is balanced out. So I just want you to note that the condition for equilibrium is just that the net force is 0, which just means that the object can be stationary or it can be moving at a constant velocity. So both of these can mean that something is in equilibrium. So that's something that can be very easy to mistake, is that you might look at something that is moving and you might be like, okay, because it's moving, it's not at equilibrium, but you should look at whether or not it's accelerating. If it's moving at a constant velocity, then you know that it is in equilibrium because there's no overall force in one particular direction.
But are we supposed to have a motion graphic organizer?
No, not today, not today.
Okay.
Today is more visual, less writing based. Okay, so why am I introducing the word equilibrium? Because sometimes it just makes more sense to look at things in terms of equilibrium. In this particular case, we have a 7 kilogram mass hanging from the ceiling. So because it's hanging from the ceiling, it's not moving at all, it's just staying there, which means that we can safely say that it's in static equilibrium, which just means that the net force is 0. So if the net force is 0, it's something that is in static, so the object is in static equilibrium, which means the net force is 0, which means that all of the forces should cancel out. So knowing that all of the forces should cancel out, what would the force of tension in the rope be? So we've done this problem actually quite a few times, but this time we are just introducing a little bit of different vocabulary, looking at the same problem. So in this particular case, it's in static equilibrium, so there is no net force. So what would the force of tension at the rope? So in this particular problem here, it's in static equilibrium, which means that the net force is 0. So this means that all the forces have to cancel out. All the forces have to be balanced. So if we were to draw a free body diagram here, we would just, I'm not going to draw it just because I think we've done this quite a few times. There are two forces here. We have the force of tension pulling it straight up and the force of gravity pulling it straight down. Because the forces have to balance, because it's in equilibrium, this means that the force of tension needs to equalize the force of gravity going down. The force of gravity going down is just mass times gravity, so 7 times 9.8. So you'll get that the force of tension should equal the force of gravity, which will equal 68.6 newtons. So nothing crazy. We've just a little bit of different vocabulary. It's just good to recognize that when something is essentially not changing, there's no acceleration, it's just in equilibrium. So now comes the part where things get a little bit crazier. So in this particular case, in this particular problem, this object, the same object, the 7 kilogram object, is still in equilibrium, but this time it's hanging from 2 ropes instead of 1. So how would you find the tension in the ropes? So before I throw you into the fire and say, figure this out, what I first want you to do is I just want you to draw a free body diagram of the hanging object. So what forces are acting on the object and in which directions? So there are 2 ropes pulling on it. They're both pulling it on an angle. And then there is another force, another maybe one or I don't know, other forces acting in the problem. So I want you to draw a quick free body diagram of the object with the forces that are pulling on the object. So you don't need to solve for the tension yet. I just want you to draw a free body diagram here to help you visualize all of the forces in the problem.
Is the object horizontal?
What do you mean by
that? Like, we see a box here. Would it be totally horizontal or does that not matter?
Yeah. It'd be perfectly horizontal. Yeah. Let's take another minute or so to draw a free body diagram here. You don't need to solve for the tension yet. We will save that for a second from now. Just for now, draw these. Let's draw a free body diagram. You don't need to turn this in anywhere. This is just, you can just do it on your notebook. You don't need to turn this in. Because because this phone is super drawing based, it just doesn't really make sense to do it on a Google Doc. So you should just do it in your notebook. Yeah, because it's gonna be very drawing based. It's like pretty hard to like draw stuff on angles and stuff. So yeah, let's just draw a quick free body diagram for this object. Hanging from the ceiling with two ropes, so we have the force of gravity going straight down. And then we have two ropes going up. There's one rope pulling up like this. And then we have another rope pulling this up like this. So we just have three forces here. One force of tension pulling this way, one force of tension pulling this way, and the force of gravity pulling back. So I am labeling these as high tension tension, 1 and 1 and 2, because it's just good habit to assume that things don't necessarily have the same tensions. They may or may not have the same tensions. If they do have the same tensions, we will be pleasantly surprised. But I think it's better just to be prepared for stuff that has, be prepared to have different tensions. And be pleasantly surprised if it does work out, if they have the same tensions. So this is just your free body diagram. It's nothing crazy, right? 3, 4, 2. However, this is not super helpful for us right now. Because these two forces are at angles. And using forces that are at angles are not very, it's not very easy, very undoable. What we want to do is we want to break down these forces into parallel and perpendicular components. So what I'm going to do is I'm going to break down each of these tensions into perpendicular and parallel components. So the first one, I have a tension force coming with an angle like this. And I basically want to figure out how much of this force, this tension force, is being used to pull the object horizontally, and how much of it is being used to pull the object vertically. So I'm going to draw my little right triangle here. And it's, oh, yes, I'm actually drawing this wrong. Tension force here, I have my alpha here, that it's being pulled at an angle like this. And I want to figure out how much of the force is being used to pull the object horizontally, right? It's essentially my X force, and how much of it is being used to pull the object vertically, essentially my Y force. So using a little bit of trigonometry, I know that the cosine of this angle, cosine of alpha is going to equal my adjacent over my hypotenuse. Rearrange this a little bit. This just means that my X force is going to equal my tension force times cosine alpha. If I want to figure out my Y force, I'm going to do the exact same thing, except instead of cosine, I'm going to use sine. So the sine of this angle is going to equal my opposite, my Y, over my hypotenuse, which is 1. And so my Y force is just going to equal tension 1 times sine. And now, if we were to do this for, and we can also do this for the second tension force for T2, and we will get that it looks pretty much the same. That one of the X is going to be times cosine alpha, and the Y is going to be times sine alpha. So if I were to actually redraw this in terms of horizontal and perpendicular components, it will actually look something more like this. I will have the force of gravity coming down, this is my change, but this time I will actually have the tension force pulling straight up, that is tension 1 and sine alpha. So what I did is I broke down this diagonal force into a force that goes straight up and then a force that goes horizontally. The force straight up is tension 1 times sine alpha. The force horizontally is tension 1 times cosine. I can do the exact same thing with the other diagonal force. So the other diagonal force is going to force straight up with tension 2 times sine alpha. It's more force here to the left with tension 2 cosine. So now I turn this problem that previously looked very nasty into one that we know we can do because we've done this. But all the forces now are either parallel or perpendicular, so we can now solve this problem. There are a few forces here, but I know we can solve this because we've done it before. Okay, so now let's try to quickly solve as much as we can. So our goal here was to try to solve for our tension force. Let's try to solve it. So the first thing is this particular object is in static equilibrium. It's not moving, it's just hanging from the ceiling. Because it's in static equilibrium, what this means is that all the forces have to cancel out. So all the forces in the y direction have to cancel out, and all the forces in the x direction have to cancel out. So that means the sum of all forces in the x direction should equal 0. The sum of all forces in the y direction is also equal 0. So we are going to start off with the x direction because there's only 2 forces in the x direction. So this makes sense to start with that to go easier. So the sum of all forces in the x direction is 0, which just means that the force going right minus the force going left equals 0. Which is just a long-winded way of saying force going left equals the force going right. Which makes sense, right? Because at static equilibrium, it's not going to be going right or left. So the forces going left and the forces going right equal each other. And then if we just cancel the cosine out, they're the same. We're going to put tension 1 is going to equal tension 2. Right. So we initially went in expecting these tensions to be different, and we were pleasantly surprised. We found out that both of these tensions are the same. So it turns out that if there are ropes being pulled at the same angle relative to the object, they will have the same tensions. However, if we notice here that if these 2 angles were different, if one of them was, let's say, cosine beta, and this one was cosine alpha, then you know that the tensions are not the same. So that's why I think it's just a good habit to just assume the tensions are not the same, and then being pleasantly surprised if they are. So now we know the tensions of the rope are the same. So if we can figure out one tension, we will know the other. However, we have done all we can in x direction. There's nothing else we can do here, which means we need to move the y direction. Let's move the y direction here. The sum of all forces in the y direction is going to equal 0, which means that the force is going up, which is tension 1 sine alpha plus tension 2 times sine alpha. This force of gravity is equal to 0. The force is going up minus the force going down equals 0, which is a little long-winded way of saying the force going up is equal to the force going down. Okay. So what do we find out? Previously, the tensions are equal. So this is just another way of saying that 2 times tension 1 times sine alpha equal to gravity. So if I want to solve for my tension, I just go to my tension 1 is going to equal force of gravity over 2 sine. The tension 1, the tension in the ropes is just going to equal the force of gravity divided by 2 sine alpha. So this is how you would solve for the tension in ropes that are in. Should you memorize this formula and remember it for the end of time? No, you 100% should not memorize this because this will change so much depending on the problem. So instead, I want you to think about how you can set this up. The general principle is the same. You have draw your body diagram with all of your forces. Break down all the diagonal forces into perpendicular and parallel components. Once you can do that, you can then just solve for the individual. So this honestly, once you look at it, it's honestly not that much different than doing a problem on a ramp. The problem on a ramp, you have forces that are equal, and all you have to do is break them down into parallel and perpendicular components. After that, it's just like any other force problem. Okay. So that is pretty much it for today. We will pick this up on Friday. We still have a little bit left. We just have one more example left, and then we will start another fun assignment on Friday. So that's pretty much it. You don't have any homework. So yeah, that's it. I'll see you guys on Friday.
Thank you.
Bye.
Thank you.